So today we will discuss experiment number 8 related to the Photonics and Spectroscopy lab, where the aim of the experiment is to determine the wavelength of the laser light by using transmission grating and to determine the number of lines in a transmission grating. So this arrangement is our transmission grating, where we have 3 different transmission gratings with different number of lines per millimeter. Okay. This grating has a number of lines, 100 lines per millimeter, whereas the second one is 300 lines per millimeter and the last one is 600 lines per millimeter. So what we will do is we allow light from the helium neon laser to fall on the grating. I have chosen 300 millimeter lines per millimeter, okay, and the pattern will be obtained on the screen placed here. So a transmission grating is basically an optical component which produces a spectrum of light due to diffraction. And we know diffraction is a phenomena where the bending of light takes place when it encounters an obstacle whose size is comparable to the wavelength of light incident on it. So in the grating, what we have is plain glass is taken where rulings are drawn with the help of diamond point, and wherever the diamond point is ruled over, that gets scratched, okay, and the space in between the rulings act as slits. So here there are suppose n number of slits here, where n is large, then each slit produces its own set of diffracted waves. As such, what happens is, when we allow light to fall through it, then the n number of slits diffract n number of waves, and these n number of waves interfere at the screen, okay, producing a pattern as shown here. Okay. So we are seeing a pattern here where this is the central maximum, okay, and this is the first order maximum to the left of the central maximum, and this is again the first order maximum to the right of the central maximum. There are other orders also available, but these fall beyond the purview of our screen. So if I allow my screen to move here, I can see I am seeing the second order to the left, and if I go this side, I am seeing the second order to the right. Okay, since we are not able to get the other fringes, so here I will use this particular grating to determine the wavelength of the laser light. So what I will do is I will measure the distance between the first order maximum and on both sides of the central maximum. So to do so, what I do here is find the midpoint and make a mark. This is the mark for our 0th order or the central maximum, and similarly make a point here where I get the first maximum in the left side and first maximum on the right side. Okay. Thereafter, what I'll do is I'll measure the distance. I'll switch off the laser light, measure the distance between the central maximum and the first maximum on the left, as well as central maximum and first maximum on the right, and then find out the average of it. So then we know that for a diffraction grating, the maximum will be obtained where d sin theta is equal to m lambda. D represents the grating element, which is equal to 1 by number of lines per centimeter. Theta is the angle of diffraction for the mth order maximum, and lambda is the wavelength. So if I measure the distance between the slit and the screen with the help of a scale, then I'll be able to use the formula tan theta is equal to y by capital D, where y is the distance between the average distance between the first maximum and the central maximum, and capital D is the distance between the slit and the screen. So using that formula, I'll be able to find out theta. Once I have found out theta, I'll use the formula d sine theta is equal to m lambda to find out the value of lambda. Here m will be equal to 1, and d, since I have here the number of lines per millimeter to be 300, so it will be 1 by 3000, where we have taken d to be the number of lines per centimeter. Okay. Then I'll tabulate those values here, find out the value of lambda. Once I found out the value of lambda, then I'll work out with the next part of the experiment, where my objective is to determine the number of lines in a transmission grating. So for that, I take another arrangement, another transmission grating for which the number of lines is different. Then I get a diffraction pattern here, and here I see that I am getting a large number of maximas above the central maxima. So this is my central maxima. This is my first maximum on the left, second, third, fourth and fifth. On the right, similarly, I have got the first order, the second order, the third order, the fourth order and the fifth order. So what I'll do is, again like the previous experiment, I'll locate the maximum with the help of a pencil. Locate the first maximum, second maximum, third maximum, fourth maximum, fifth maximum. Similarly, locate the first, second, third, fourth and fifth maximum on the right as well. Then what I'll do is, after switching off the light, I'll measure this distance between the central maximum and the maximum in question with the help of a scale and tabulate it and find out the average distance between the central maximum and the first maximum, or the central maximum and the second maximum, and so on. So I'll have 5 data in all, from which I'll take the value of the wavelength as what I have calculated from the previous observation. Having done that, I'll now use the same formula, d sine theta is equal to m lambda, and use the to find out theta. Again, I'll use tan theta is equal to y by d. Once theta is known, I know d sine theta is equal to m lambda. Now I take d to be the unknown, and theta will be what I have computed from the observation, and then I find out d. Once I find out d, I can calculate n, which is just 1 by d. Okay, so that is how the experiment will be done. Once I have computed the values of n, what I'll do is I'll find the percentage error, because number of lines will be provided to you from the lab. So once you have that, you will calculate the percentage error. The percentage error will be with the actual value minus the experimental value by the actual value into 100. So now, since this is an experiment related to laser, so care must be taken that you do not stress your eye, or you do not allow light to fall on your eyes. The other important thing is the there should be a perfect alignment between the source, the slit and the screen. They should all be in the same straight line. You should not disturb the table while you perform the experiment. And the most important thing is this experiment has to be done in a dark room, here only to make you all see how exactly it's happening. We have done it in light, but in actuality the experiment has to be done in a dark room where you do not switch on the light.